stock, others may not have, hit. And so I'm going to talk to you about the properties and characteristics of ultra-small silicon nanoparticles, and maybe present some applications of advanced technologies. Some of them biomedical, others are not. Okay? And I am a professor at the University of Illinois in the physics department, which is located in the College of Engineering. Not too many universities in America, physics is in engineering. So this is in engineering. And also I'm the president of two companies, startup, small companies. One of them is called NanoSci, for nanosilicon, advanced technologies. And the idea is to promote the nanomaterial and to get it to market, commercialization. The way we produce the nanomaterial is we start with commercial wafers, silicon. This is a bundle, $18 a piece. And we have developed a procedure where we use common chemicals like acids and hydrogen peroxide. The acid is HF. And we use low energy requirements, and sometimes we use zero even current, to break up this wafer into a family of ultra-small silicon nanoparticles, and they actually produce under dark light different colors depending on their size. This is not a good picture, but the smallest one, 1 nanometer, is blue luminescent. The next size is green, and the other one is yellow-orange, and then red. These are the spectrum of the nanoparticles we produce. This has several patents covering this. It's an electrochemical process. The process in simple terms like this: you have a wafer, a piece of the wafer, silicon nano, and a counter to it, and on the other side of the HF, H2O2, and methanol to absorb heat, we have a platinum electrode. Could be mesh, could be wire, could be cylinder, and a current is set between both, and between the HF and H2O2 and the current, you make this like Swiss cheese. Very, very tiny, ultra-small nanoparticles are produced. After an hour, 45 minutes, you remove this piece and shake it in a liquid, then the nanoparticles come out. We actually have a motorization. We push, there is a motor that pushes this wafer deeper, deeper with time. So to allow us to process a large area for mass production. This is a small model of the device, home-built in the department. It's Teflon here. There is a complicated, there's computer control, there is a motor in to move the sample up and down. This is 20 by 20 centimeter. We've been, the company sells the nanoparticles, but not to individuals, mostly to companies, big companies, to make joint projects. For example, with Samsung, with Polybrite, with Wintec, with Sharp, with Panasonic, to develop together devices. Another procedure we're using that eliminates, because you're all trying to make it faster and cheaper, is instead of using a current, we use a catalyst, this kind of catalyst. And first we process it here to produce platinum nanoparticles to get onto the surface of the silicon wafer. Then we move it to the essentially the same etching procedure. And then you take it to the third bottom and shake it, and the particles come out. Okay? Here are some examples. DM, high transmission electron microscope of some of the particles that are produced. Here, zoom in on some of these particles. In the lot, this is the 1 nanometer. This is the next 1.7. This is 2.15. This is 2.9, or sometimes for simple we call it 3 nanometer. This one is a larger one. It's an infrared particle beyond the red. So you see, it's RGB, more like RGB. We cover that. Here, some zoom in on the 3 nanometer, and you could see the atomic plane inside of it, and you could see how uniform, and here more images. You can produce a soup, a mixture of these 4 sizes, or you could choose your conditions such that you produce one size and nothing else. Okay. So for demonstration, you can produce a soup and separate them in bottles like this. Here are the red particles in a very big jar, and some smaller. This is just for fun. If you want the smallest one, welcome. If you want the larger one, it looks like Kool-Aid, this drink. The smallest one has been attacked by many theory groups. Maybe 10, 15 theory groups. And now we believe it is a silicon 29, a magic number. The orange is silicon, and it is hydrogenated, only on the surface, not on the inside. So the larger ones, they will have hydrogen on the outside, but not inside. So it's not like amorphous. It's a shell around it. This is silicon 29, 24 hydrogens. And you could think of it as there are 5 of the silicon atoms don't have hydrogen on it. They are on the inside. 1 tetrahedral unit of silicon on the inside, and then the shell of 24. Some theorists like to call it silicon 28, and 1 down the center, and the 28 is like a fullerene shell. So they look at it as a fullerene shell, with 1 extra down in the middle. Okay? Whatever, that's the important thing is that you could have them in bottles like dye and the other size. And Yulia is going to turn on our device here, which shows some of them. I had to smuggle the liquid with me, and I put it with my shaving cream, and I thought if anybody asked me, I would say this is for cosmetic. And indeed, I visited L'Oreal some time ago, and they've been considered for cosmetics. I may have a slide on that, maybe not. So you could leave it on. Here's a summary. Ultra-small silicon particles, 1 to 4 nanometers in this range. We produce them. Discrete sizes, a family, discrete sizes, highly fluorescent, and distinct color RGB. So the fact that there is an RGB spectrum opens up a lot of applications in electronics and in biology. This is an image of the particle made by Livermore National Laboratory, the theorists who work on this one. What happened to it? The material is so bright compared to the original wafer, because the original wafer is dull. The dullest material in the universe is silicon, because it's indirect bandgap material. So Nature News wrote an article under the title "Let There Be Light" from the Bible, that the universe was dark, and then one day light came. And so they consider the silicon wafer as like the dark, and then the nanoparticles light came out. You could study them with different techniques. Here is autocorrelation spectroscopy, where you put them in a liquid, like the stuff we have, and you focus a laser beam 780 nanometer, femtosecond, 100 femtosecond. You focus it like this on the tri-cipher laser. You focus it right here, and here is an enlargement. This is the focal waist of the beam, and we choose a density of the particles low enough such that on the average, only one would be in the waist. So in and out. This guy is in now, it comes out. Then this guy goes in, then that out, and back and forth. So between diffusion and that, now this is a well-established techniques. So you could quantify the density and also the size and the diffusion coefficient. And this allowed us to claim that we can detect a single one. If you can detect light from only one of these nanoparticles, that means you can label DNA, you could put it on a tag and so on. So that was the idea. Lifetime, the 1 nanometer, after being excited by a femto or picosecond laser, now I must say that they've been excited by 780 nanometer from this femtosecond laser. But 780 nanometer, one photon of that will not be able to excite the particle. But the particle is becoming a nonlinear device, a nonlinear material. So it sums up two photons, 780 plus 780, to produce like half of that, 390. So as if we excited it with 390 nanometer, one photon. And also it is good, yesterday we had Professor Valerie Tuchin, who was talking about the multiphoton excitation, and all that is really in here. Okay? All the advantages of two photons, a small focal point, no damage to biological, all that. So now the lifetime of the 1 nanometer, the smallest, is 2 to 3 nanoseconds. So it's very fast. The red particle has two lifetimes, one in the 2 to 3 nanosecond, and another piece, which is tail, which carries almost 50% of the light, has 50 to 100 nanosecond. So this is also, could be fast. You could use it for gating if you have another phenomena with microseconds. So you could use time resolution to discriminate against other things. The 4 particles, you could study them individually by putting them in a bottle like this, shine an excitation, and look at the emission at right angle. And you could tune across their absorption or their emission spectrum and find their band gaps. Of course, a big wafer has a band gap of 1.1 electron volt. But as you miniaturize and confine the electron inside the band gap, you produce discrete levels, and those discrete levels add their energy to the 1.1, and so to the degree where you can add enough to get to the red, into the blue, and all of that. And so we can study their band gaps, and here is an attempt to study their band gaps, each one. So in principle, you could excite each of the particles, all of them together at the same time, with a single photon in the UV. Why is this so? Because all of them are made of silicon. And it turns out that you could say, what is the smallest piece of silicon that you could measure and identify that it is silicon? It turns out 1 tetrahedral unit. If you have 5 silicon atoms together, you can tell that this is a silicon piece, solid. And so all of them have units like that. And so you could excite them with a single UV. You could excite them with a single photon also, but each one around its band gap. Okay, so UV, then maybe you excite one with the green, maybe one with the yellow, maybe one with the red. You could excite them, but all of them will be excited by one single UV photon. Third, you could excite them with 2 photons, near infrared, femtosecond, between 720 to 900 nanometer. This is a popular and they sum up. The material is different than the original because it's ultra small, the atoms have moved from their original positions. So there is non-linearity. You could excite them with the electron beam, with electrons, and produce electroluminescence. We've been trying to do that, and most recently we had some project with Sussex, and we measured some the red particles of Sussex, and we've seen some signals like that. So this was published 3 years ago. If you take like the particles in the liquid like that, in the liquid you see it's for preservation. Because they're too small, and if you put them in the table, you can see them, they're lost. So in a liquid, you could use them for later delivery. You know that they are there. And so, but now if I take some of it and I put it on a piece of glass, the liquid will dry, and you get the nanomaterials in it. So this is one case, you produce ugly clusters. Sometimes you produce beautiful ones, and we have those. And each of these clusters now starts to act a cavity for laser action. So if you excite this one with this infrared femtosecond perpendicular to the page, then one edge acts like a mirror if it's looking nice, and the other edge looks like the other side of the mirror. And you can see here the resonator. This is one edge, this is another edge, and there is a blue beam in between. So we're exciting with infrared, and blue light is coming out. Just like yesterday's talk or the day before, substitution is starting out. Okay, and so in a liquid, the excitation is 2 photons, so it's quadratic if you do intensity versus incident power. But in this solid here, look what happens. There's a very sharp 6th order of magnitude enhancement in the light coming out. So there is nothing, and all of a sudden the threshold, and then it saturates. So this is like almost a laser reaction. They're photostable. You can study them in a gel, like here. You immobilize, there are circles here, and the circle inside of it, the circle is used to tell you there is inside of it is the particle. So this is a gel, and the particles were mixed in the gel at low density. Here is a quartz, and this is a dye, a small density of dye, and this is the nanoparticles on a similar quartz plate. And you shine the laser beam perpendicular to this or that, and measure the emission and see. So here are the nanoparticles. They keep producing the light. We went to lunch and we came back, and they're still producing the light. The dye, like in this case, they die. That's why, see, this is 1 second. After 1 second of this infrared femtosecond, it quenches, it bleaches. Whereas this one, you can see is different. This is under UV, very harsh laser beam, and the dye just dies like this dye, and the nanoparticles produce maybe lose 50% over many hours of this harsh. Now, because I told you there is a hydrogen on top of them, there's a silicon hydrogen, that means bond. That's very important, unlike many, quantum dots or nanoparticles. Now you can utilize the silicon hydrogen chemistry in order to make them smart or interface them with biology. For example, you could put them in OH groups, or carbon with a tail, empty, which means you remove the hydrogen and you put a silicon hydrogen bond now with a tail, or you ionize them, or you put carboxyl, or a fire group, or rings. You design chemistries. In fact, the chemist who was first to fool with this is Illinois. She's originally from Russia, but she worked in my lab as a postdoc. Here's the scheme she came up with. I'm not a chemist, but This is, so you start with silicon hydrogen, the red shell is the hydrogen, and you come in with this compound. It's a double bond on this side and a carboxyl on the other side. Now, because it's a bilinker, this one is active, reactive, and that one is reactive. So what she did, she removed that hydrogen and put a metal group to protect it. Because we don't want the carboxyl to attach to the nanoparticle. We want the carboxyl for later, for biology. And so, you know, she did this chemical reaction, and at the end, she removed that metal group and put back the hydrogen, and now the particle has a silicon core on the inside and all these stains, a carbon bond attaching, and a carboxyl on the other side. So it's ready for reactive doing things. Here is aminization. You start with the silicon hydrogen and you chlorinate it with the chlorine gas. So you remove the hydrogen and you put chlorine. That's the first step. And then you come in with a compound of interest, like in this case is butylamine. I don't know whether you can see this. The colors makes it hard to see, especially when the light is not there. And now you end up with the particles where you have an amine group attached to them. Again, you know, if you know silicon hydrogen, and the idea, don't touch the silicon itself, because if you touch the silicon, you ruin the particle. You only touch softly the outside. You remove this and put something else. Now, there may be some changes, and you know, there's a lot of theory on that and measurement. Whether putting that carboxyl on it would shift the emission, the absorption, all of that. The nitrogen tends to shift more than anything else. But all of that is tabulated, and we already have it, theory and experiment. Here is a thiolation where you put the sulfur over it. And this one is a similar scheme to the carboxylation, but you know, all these complicated ones are side effects, and you're trying to minimize, you're trying to prevent this from happening. So you end up with where you want. And these are also sulfur bridges making. So once you put sulfur on it, it's very sensitive to air, very sensitive to oxygen, and so you have to do it and do your experiment, otherwise it comes. Here is a theoretical model, a quantum Monte Carlo. In other words, now, if you study the particle itself before and get you know, these theories, once you put on it this tail, it's not your particle anymore, because this one may be larger than the particle almost. And so you have to start the whole thing from the beginning. We put them in a quantum Monte Carlo, many body. For example, here, silicon 29, you have to add all these atoms to it and whatever, and recook the whole thing. But this was done by Lewis Meters at North Carolina State University. Here's a scheme where, let's say we have put carboxyl on the particle. So let's say one reaction, if you have a hydroxyl on it, silicon OH, and you have another material where it has like a DNA or something else with an OH, this is simply you remove water and you will have an oxygen bond. Normally, when you buy DNA from the market, the DNA is already being labeled with an amine group like that. Somebody already worked it out and they sell it. So we buy this. Now this is R2 with our silicon nanoparticle, and R1 is the DNA, or a protein with a carboxyl. So you put them together, they react, they pull out some water, and this nitrogen will connect to that carbon, and you get this connection. But it sounds very easy, but it turns out this is very complicated, and a million-side things could happen. And so what happened, a group from École Normale Supérieure in Paris came to town, and we made a group of different people from biology, from chemistry, and from physics, and from imaging. and to try to accomplish this. And before that, the scheme was, before you put them together, before you get the DNA with the amine and the nanoparticles with the carboxyl, you need to use a catalyst to speed it up so that side reaction will not take place. So you want to remove that hydrogen from the carboxyl and attach this NIS. This nitrogen is serine with the nitrogen with the hydroxyl like that. So it connects. So this is first, you prepare the nanoparticles with an additional step. Now this is the nanoparticle. The R1 is the nanoparticle. And it turns out if you now react this one with the DNA, which has an amine on it, it can interact a little bit more favorably and give you back that NIS. So this was tried, even then it was quite complicated because how you separate the DNA that did not react, how do you separate the nanoparticles that did not attach. There's a lot of action. But anyway, just to also we tried during their trips to connect it to proteins, streptavidin. Here's a theoretical picture of how the nanoparticle would look like. This is the nanoparticle size. Here is a tetramer of the streptavidin, a piece of it. And here to scale the size of a dimolecule. So it's not as bad, similar size, so ultra small. Now, in general, how do you deliver these nanoparticles if you have in a liquid? You said we store them in a liquid. So how do you deliver them where you want? And it depends on what action you want. For example, we can deliver them mechanically by dispense evaporation. I just open the bottle, pour some stuff, evaporate the liquid, or you take a drop or a float with me, those trivial things. So that's one. But it doesn't produce uniform, obviously, but that's one. You could spin coat them while you're spinning your device, you drop the material, and it does produce a little more uniform. Or using an atomizer, you put it in a bottle like the perfume, and you just squeeze, it comes out, and you do that. I was doing that at home. My wife said, well, what's happening to you? Why are you putting all this perfume? I said, or electrically based. You could use electric deposition or electric spray. But that means you have to charge the nanoparticle for them. And there are ways of charging them easy in a liquid charge, and I'll show you an example. Or because they are identical in size within each group, they self-assemble. You just put your substrate in the liquid, inside this bottle, wait, they self-assemble, you remove. You could incubate too. Even if your surface is not perfect, you could incubate, like I want to incubate a cell in the nanoparticle and see if they go through all that. What kind of substrates you can handle? You could handle conducting, non-conducting, flexible substrate, even folded, three-dimensional, or you can even make designs, patterns. In the rest of these slides, I will only focus on the red nanoparticle, of how we use it to do things. The red nanoparticle is very interesting because red light on amine groups and on cells has a good contrast. All these bodily things produce blue-green light. And so if you put on them the nanoparticle, the blue one, although I'll show you some examples, you have to work harder to say that these are the nanoparticles, this is not the fluorescence of the cells and so on. But the red is nice. The red nanoparticle, if you excite it anywhere between even 254 deep in the UV or even lower, we took these particles to Darsbury synchrotron source in the UK, and we studied deep wave in the UV. But you produce red light, and here is the spectrum. It doesn't change. Okay? This is the spectrum. And our procedure is not sensitive to, the Yulia did it or the other Yulia in my lab over there. It doesn't matter. Although their names are the same, but that's not the reason why it comes out the same. Just like that. And you see the bottom like that, red. And these are some good attributes. The contrast, of course, the hydrogen chemistry is already, and of course these particles are silicon-based, so they are the least toxic quantum dots or nanoparticles. In fact, they dissolve in the body to produce silicic acid, and that's even needed. Here's one example where you fill a nozzle, a conducting nozzle, with the liquid in some of this bottle, like that. And you fire it up with 2 to 3 kilovolt. And then the alcohol, of course, if you have a speck of water, of hydronium, then it gets ionized, and the ions land on the nanoparticle, and the nanoparticle becomes ionized, and they shoot out like a spray. And you could make patterns directly where you want. And the high voltage does not ruin the particles, so you could see them inside under the ionization condition, and they're luminescent, and even after they land, the same. So you make them land like a uniform, or you pattern them, or you do. You could push them inside of a liquid like this. You put electrodes, cathode, anode, and the nanoparticles in a liquid like that. When they start going, carrying a charge, a hydronium or the other, the negative charge, and they start moving. So it's like you're plating, like you plate utensils with silver ions. You remove this one and this one. And if you have assume that all the sizes that do green and that, they self-assemble. The red ones go together like this, and you see they're making beautiful crystals and stuff like that. And here is the atomizer, in case a voltage ruins you. So this is making thin layers for solar cells, for example, worked up very nice, like that. Incubation, here is, we've incubated sodium chloride crystals. This is a project for Argonne National Lab. They wanted to improve the detection of Cherenkov radiation. And so we incubated sodium chloride, and this is coated with the nanoparticle. This is not. So under UV light, this one is red, that other one is not. Under white light, both of them look the same. And you could study the spectra and the shifts. You could even put them on carbon nanotubes by incubation. Put the carbon nanotubes in this liquid, in this bottle, and wait a little bit. Take the carbon nanotubes, image it, and you could see that this is a high resolution image, and you could see the thing on decorating the carbon nanotubes. Fiberglass, you could take industrial fiberglass. Here the fiberglass under UV is nothing because it's glass. It looks blue. But when you incubate the fiberglass in the nanoparticle, they coat it and producing this color. Now you could use it as some kind of a sensor. So here are two pieces of the same fiberglass. You put one of them in H2 and amine on this, but no double bond. And double bond here and then H2. This guy attaches and the amine produces blue, light green. Superimposes the red, starts to look white. The other one, no, which means doesn't attach. So you could see visually with your eye as a sensor, or you could put, of course, a detector and look at a more serious thing. So in general, now we want to encapsulate them because it turns out that it may be a need for making them larger, for protecting them, because we're all afraid of nanomaterial, but nanomaterial themselves are afraid of us, because if you put them in our body is poisoned to the nanomaterial. So it works both ways. So we want to protect them. And this is a project actually motivated by Dmitry Gorin's group. Over the last couple of years we've been working together on this. So luminescent nano micro capsules, and there are several applications. Of course, imaging tracking, underground oil or water. I have a project like this where I put them in polyethylene for an oil company, an Aramco, American oil company. You could use it for biomedical or drug delivery. And in principle, you could maybe interrogate them electrically or magnetically if you add some magnetic material. And the nanoparticles are polarizable. That also helps. Here, for example, is we encapsulated them in polyethylene, a conducting polymer. And so on the average, they're inside. And this is done simultaneously while the polyethylene is produced, so a micro or mini emulsion process. Not that if we made this and pushed the nanoparticle inside of it at the same time. And this is a TM image of some of these capsules, and you can see the dark core, which is the silicon. And then you can see the lighter, which is the organic material. The idea here is to produce about 100 nanometer diameter nanoparticles. They don't want smaller, they don't want much larger, because this size, 100 to 200 nanometer, is the size of pores in rocks where oil is. Apparently, oil is in porous materials. I thought it's a lake, you know, but then when I visited with them, they said, oh, no, there is no lake. It's all in rocks, and it's all like pores. So we want to, this is a rock, in fact, a picture of a rock. So we want to push these nanoparticles from one side and look outside and interrogate the material and see if you can affect anything. So a group in Saudi Arabia are enclosing them in a silica shell, and in Illinois we're doing it in polyethylene. We're exchanging that information. Here is in another polymer for drug delivery, and this is what also Yulia, under the direction of Gorin, they're doing. So we prepare the calcium carbonate structures, micro structures. They could be amorphous or crystalline looking. If they are amorphous, they have pores. Then we incubate the nanoparticle. We put these in the nanoparticle solution like that, and wait. By the time you know it, they're moving inside of it. And when they move inside of it like this, they color the calcium carbonate. This under UV they become colored. So you know that now they are impregnated. Now the question is, what is the attachment, the physical attachment? The silicon hydrogen with the negative charge on the calcium carbonate, and so on. We're doing some detailed study right now. So you could put them under a fluorescent microscope, or you could see it with your eye even. Of course, the idea is that if you could add more ingredients, you could put other molecules, other drugs, and then you need to encapsulate, and the calcium carbonate on the average, this is a polymer, and you incubate again, and you put a coating around it. Now, how does this polymer interact with the nanoparticles? If the nanoparticle is already making a shell around it, what is the charge of the nanoparticles? What is this charge? And you have to play some games. Here's the emission of this polymer, blue-green. The nanoparticles are red. So in principle, you could do characterization. Is the polymer on the nanoparticles or not. You could do optical spectroscopy, or you could do other things. For example, here is the blue-green and red nanoparticles. You can see it optically. And here is an XPS. You could look for nitrogen. You could get these clusters out, dry them, and then use XPS, and we see a nitrogen peak, which means there is green blue light correlates on the nitrogen, so it is there. Then you could dissolve the calcium carbonate and try to see if the polymer stays intact with the nanoparticles inside. And we have seen cases where we lost some signal because maybe this polymer is not retaining them 100%. But that's why we have to do more work and put more layers. And as you heard from Professor Gleb yesterday, then you have to use some remote procedure to break this on demand, whenever you want. Okay, at the point, at the time you're interested in, and release whatever inside the node. The nanoparticles are nice because you could track what you're doing. You could observe as the capsule is moving, or if you break it, you could do diffusion studies. You see how they spread in a certain organ. Or you could add some magnetic stuff to them by pushing some ions like erbium or iron inside the particle, and this is a theory, a full-fledged quantum Monte Carlo calculation, quantum calculation. But in my group, I mean, we learned how to do it. First, the theorists were doing it, then we just softwares, and if you just put enough time, you could figure it out. And we found two positions. One, the ion is just outside, and one just inside like that. And we just studied that experimentally. Now, here's a breast cancer for imaging and sensing as an example. Breast cancer is usually rough, very rough, and eats everything. That's why it's cancer. So the nanoparticles went inside, and you can see the coloration of the blue nanoparticles. And this is an E. coli, an image with a TEM, and also we were trying to stain the E. coli. This is a kidney from a dog. The red light is actually not the nanoparticles. The kidneys are very dark, you can't see. And so we shine a laser beam on the kidney, red laser beam, in order to see them. And then, but the green is the nanoparticles. In fact, we found that the nanoparticles produce a second harmonic signal. So they have spectra where not only they produce the emission, but then if you get the right angles of that, they produce a second harmonic. So here is the stem cells done in veterinary school. My friend pushed them inside stem cells. The idea here is, it's not just just mixing and doing that. There is real schemes of how you attach the nanoparticle, the silicon hydrogen onto an E. coli, and there are real schemes. We're trying to make a pregnancy test by attaching this to and show that you could test for pregnancy faster than normally, because in America they are very conservative, and if after 2 weeks you say there's a pregnancy and you want to get rid of the child, say, oh, life has formed. And so everybody now is trying to speed it up, so you could say, oh, no life yet. So you do that. You could use it as a glucose sensor. Here is a comparison between an enzyme. This is an enzyme. So it's an electrode. You put an enzyme over it, appropriate. This is well-known standard technology. And we use a similar one, but with nanoparticles on, and compare both. And it turns out the nanoparticles can break up the sugar and give you a signal. This was voted by Nature magazine as one of the highlights of the year. And the nice thing about this is that you get the signal right away. Okay, so you could implant it and interrogate it wirelessly, maybe. So, you could put it on hair, human hair or otherwise. Here's this is here with the eye, a camera. You just use your own camera and your cell phone, and the hair looks like that. But here with the fluorescent microscope, and you can see it's going in more or less in various places, concentrated in some places, but others damaged places, maybe reticule edges. So you could do all sorts of things, antibacterial, static charge, make you more beautiful, lighting effects, that is, repair, all sorts of advantages. Here's a project with a women section of the university in Saudi Arabia where there's ovarian cancer is in the late stage. And here's the drug which is called, what is it called? I always don't remember the name of the drug. It's docetaxel. And this drug, this is like a head and a tail. And this is the guy which divides and produces, the cancer. And so this drug is supposed to come and wrap around this one. And once it wraps, it connects around it, the tail slides around it, then it stops it from doing that. And so the idea was to attach the nanoparticle on the tail like that to monitor what's happening to the process. Of course, attaching the nanoparticle like this on this one may ruin the drug. So there's a theorist who's trying to understand what happens to the energy levels, to the spectrum, to the electronics aspect of it. You could put it inside of a memory. What is a flash memory? It's really a capacitor. Here's an electrode, an aluminum, on top aluminum, and in between glass. This is actually what we carry in our pockets. Very tiny. From here to there is like 50 angstroms. I mean, 50 nanometer, the thickness, and this wide is the same. So it's big. Transistors are much smaller than these units of memory cells. So the transistor is getting smaller, but the nano memory is not as fast. So you want, so what we did, this is a project with MIT. They implanted the nanoparticles inside the glass, like this. They don't have to be in an array like this. This is just a good picture. And instead of using the random oxide inside to store, because the information is stored as a broken oxygen from the glass, a bad oxygen, a bad bond. Now you have well-defined the amount you want and put it where you want, and it turns out it works and better than originally, and you could allow this to shrink in depth and make it smaller. You could shrink it to 10 nanometer instead of just 50 limit. Because you don't need the glass anymore. You have concentrated the places where the electron land and you store. So the information is stored on the nano, not in the glass. So you don't need the rest of the glass in principle. You need 10. Here, which is the same idea, is that, remember in E&M, electricity and magnetism, the capacitance of an object is 1 over the radius of the sphere or that. And so with the nanoparticles, they have a big capacitance, so they can store a lot of charge. That means you can make a better capacitor, a supercapacitor. So what we've done, here's a brush. And we mix the nanoparticles of this liquid with some polymer or something, and we painted a very thin plastic sheet. On this side, turn it around and do the same. And the nanoparticles act as the metal, and the sheet acts like the stuff in between, the non-conducting. And this stores a lot of charge and helps you in solar energy if you're doing. And here is, look at this tiny piece from this sheet. And it fires up a panel of many, many LEDs, and you could read. And this is all based on storage of charge. Here you would take a commercial BP, British Petroleum solar cell, and put a layer of these red or blue nanoparticles over it. And then you could, and as the sunlight strikes this one, now the sunlight is intercepted by the nanoparticles first before they get to the solar cell. And so the red light that's coming from the nanoparticle hurt the solar cell, because the solar cell likes red light, doesn't like other, it's not efficient. And secondly, the charge inside the nanoparticles could be separated without the light coming out. And so you enhance the solar cell by adding these layers. And you could make this polymer I told you about, conducting polymer with the core inside of it as even a new material for photovoltaic. It's not only for imaging, because this is a conducting and a different material, so we tested the pen and it turns out it allows to capture more of the sunlight. You could make a supercapacitor instead of a sheet, a wire. Like this, this is from your lab. You've probably seen a spool like this, and you make it go through the red nanoparticle, and you coat that wire, and now you produce a wire which has nanoparticles over it. It turns out this is like a supercapacitor. You could use it on a thread and put it on a shirt. A military man or somebody going to the analyze could put all his power on his shirt, and very light, flexible. You could mix the RGB to produce white light. On last Thursday, I was giving a talk to Dow Corning. They're interested in this, the company. The phosphor, we use this, I don't know whether you will be able to see from a distance. Do you see any colors? Yes. This is like I'm trying to mimic that. Okay, I brought some samples. Okay, they do exist. These materials, which I just showed you, they are put over an LED to produce red, green, and blue light, phosphor. This is the nanoparticle. This is zinc sulfide doped with some silver or something, producing white light. And it turns out that it enhances the color characteristics, and that's why Dow Corning is interested in this. Now this is, if you study, now this is real pure physics now, there is an electron inside of these particles when you shine light on them. And whether you're producing a single state or a triple state. So we found out that if you shine a very strong UV on them, on the nanoparticles, they start losing some of their fluorescence, like that, coming down. But if you turn off the UV, then they recover, like this. And the time characteristic is several hours. So this one is going down quickly. So going down and then recovering. The important thing is the recovery is several hours, and this is, then you repeat it, and here is a multiple. And this might be good for quantum computation. The spin, we believe that the reason why they went down because they went to a triple state, as well known in chemistry, triple state, as a dark state. And we have a full-fledged theoretical calculation of the energy levels of this nanoparticle and where the vibration levels and how we explain the triple state. It's too much detail for just breaking the ice. Here we try to push the nanoparticles with electric and magnetic fields. This is important for astrophysics, nanodust. And so the same nozzle comes in, then we intersect it to the electric and magnetic field, push them, here is the magnetic field, and we were able to use a quadrupole magnetic field, focus the nanoparticles on a disk and with a hole in the middle. This is, how much time I have? 5 minutes?
Yes.
You could excite the nanoparticles, but the nanoparticles could excite kids too. So here is children, and they're very, very interested to see this and play with them and see what's going on. So here's at a school. Yes, and I invented the Dr. Nano, so I'm now Dr. Nano. I write short stories about nanotechnology and how to explain it to children and other people. Commercially, the advisor to President Obama came to my lab. The commercial or the industrial advisor, and wanted that this is from a company and this is from another company. And they were trying to, because he's Obama from Illinois. He has a house in Chicago, so you know he wants to help. Just like here, right? He wants to help the Chicago and Illinois people. Here you become a millionaire, or I was pictured with this billionaire who gave me $9 million. $9 million. And then they put me in Rich magazine because I'm standing next to this guy, next to these beautiful women. Without becoming a millionaire, but you can make it to these materials. Here the speaker, you know, the head of the House, the Parliament of the United States, came to my lab and he was looking at the particles the way you are. And here's the newspaper came and took his picture, and I'm looking at him and letting him see the nanoparticles. And the technology is protected by a lot of patents, 16 already issued and 10 pending. And my last slide will summarize, and I hope I have convinced you that the silicon nano material is a wide platform technology. Wide. What is wide? Meaning it has a lot of application in many fields. So look at this bunch in red. Electronics, nano memory, even single electronics, photonics, lasers, photodetectors I have shown you in the UV, or energy and lighting, photovoltaic, solar cells. I didn't show you fuel cells. Here is the green, and the most important thing is that it can be integrated in the silicon industry, because silicon over silicon. And hopefully you just add one step where you push the nanoparticle spray it or electron spray, you know. And hopefully it is a green technology, least toxic for consumer applications. This is my story, and thank you very much.
Thank you so much for this lecture. This question, please, Gleb.
So very interesting. I have actually two questions. The first, well, I start with the problem. There is a big problem. If you have any fluorescent dye to measure something inside cell, you need a reference. Because most of the organic dye, probably all of them, if you get it inside the cell, there is so much things interfere with their fluorescence that you can't really say whether you have a quenching of fluorescence, or whether you have excitations, or you're out of focus, or you just die. Inorganic dyes, like quantum dots, they also have their limitations. Body toxicity, also stability is not good for many of them. My question is, how stable your particles in terms of the influence of salt, pH, ion concentration, and all other things? Could they be
more
used?
Stable than quantum dots, the cadmium, selenium, cadmium sulfide.
Would they be?
Because of the silicon hydrogen, because of the hydrogen protection.
So they would be very appropriate to use as a reference. For instance, if you make a composite structure, I like our capsules with that, but you have sort of construct where you have your particles and other particles, your fluorescent particles and other fluorescent dye, which is sensitive to something, and whatever fluorescent changes, we have yours as a reference point, and we actually could be more on the right side, right?
Yes, possibly. Although they get affected by the pH.
So it's pH dependent.
Yeah, so if it's in a low pH, they're robust because it leaves the hydrogen on them. For the opposite, you have to worry. But once you know, then that's stable.
So another question is how scalable? Well, you presented in one of your very first slides. You presented how you make those particles. How scalable is this?
I showed you a jar like Kool-Aid or lemonade jar, right? It was one big jar. I have no problem in making one jar as big as this one.
Okay.
No problem. Niet problem.
No problem.
But the red one, the different ones, like some are harder than others, but the red one, you just,
Okay.
no problem.
My question, in addition to question of glare, of course, the small size of particles change properties. So, if silicon stable maybe in wide pH interval, but nanosilicon, the more wider or maybe more narrow interval. What interval? Narrow. But what interval the best from your point of view for stable the color fluorescence, for stable of maybe to aggregation?
Neutral is good. I'm saying if you have a range, if you want to, because you can never, not everything is neutral, but if you have acidic, no problem, but if you inch in towards the basic, you start having. Of course, and we don't need a layer of protection. So the size here is the size you are going to be using. Unlike quantum dots, by the time you know it, you are 10 nanometers. And 10 nanometers is much larger than pores in cells, whereas this one was very much, biologists were interested in those because, they just go through pores, for example, the 1 nanometer. So it is narrower than the big bulk, the range.
Other questions? You can use also Russian, but please, Hasan.
You told that you use the precision method for reducing nanoparticles, but you don't try it. We can use powder metallurgy or for example, mechanical alloying to reduce the nanoparticles.
We tried to use silicon germanium alloy, for example, in order to shift, because with germanium maybe we can shift these band gaps. It didn't work very well, silicon germanium. But maybe this procedure only works for silicon because also germanium itself, the germanium chemistry is the wrong chemistry. Silicon oxide is glass. So germanium oxide dissolves in water. You put it in water, it just disappears. So we try to make some alloys, but I think this will turn out to be very particular to silicon. Yes.
You show only 2 examples using the silicon as sensor, only for glucose and dopamine, but maybe there are many examples of other substances also. Not only to this.
Yes, in principle you could attach some layer on them to be to recognize many things. We have not done
This is only
too
two
many.
examples.
We have not done too many because, you know, this is...
And do you see maybe articles in which they use the silicon in the fluorescence resonance energy transfer phenomena?
Yes, this is very interesting. We got a group of us, the three of us, we got a grant from NSF to do that. So what we tried to do is to put the nanoparticle at the tip of an enzyme. That's optical near field optical microscope, and put it over cells and try to see if the energy transfer is taking place, which means short range, you could get better resolution. It didn't work, but maybe, you know, we did not really put too much effort.
Yes, I see the red color is like the European complexes, also red color.
Yes, European red color, but the problem of it is that it has sharp lines.
Yes.
And sharp lines are problematic, because then when you, for example, that's the reason why I was presenting to Dow Corning, because the nanoparticles have a smooth
Yes, I see.
color. The other one's like that. So when they mix it with other things, it shows. It doesn't mix, doesn't produce good sunlight. Sunlight is not sharp. Thermal sunlight is thermal. And so that's a key, good question about this sharp lines. Yes.
So probably just if I got it right. So if you have a dopant in your particles, it could be, well, for instance, European or others, and they would be, you know, the white band and the narrow band and sharp band together in the spectrum. Is it size change? Does size change or particle, or just like?
Size might affect that. Also, if the atom you are putting or the ion interacts very strongly for many orders of magnitude, not perturbation, it will its own sharp lines will disappear, and it will start to look like a molecular, because you have the ion next to it a silicon. And so now you can tell if it's a silicon ion, a silicon European, or silicon ion bond and things like that.
Do you control it? For instance, if you have in your population of the silicon particles, you know that you have X percentage of those ones is dopant, or you really don't control it?
Which one?
No, for instance, if you have silicon particles and you have it doped with...
Oh, the doping.
Whether you have, say, you can be sure you have 100% of them doped or not.
We just published a paper on this, the doping. We try to look, we believe it's more like a, when we dope them and we fire them with this electrospray, we're changing the charge. The ones that get doped, they have a different charge than the ones that don't. And so we see the highly charged ones going down the middle a lot, and the other ones stay outside, which means maybe there is a 90% success rate, or 85 they're doped, and 10-15% are not doped. We try to look for the sharp lines inside of them by exciting them with an electron beam. It didn't work. We were looking for infrared emission from these dopants. But we published that the thing that didn't work, just to put the spectrum, didn't show. Our argument was that maybe there is a very strong coupling and produces maybe white band. That's why we're looking for sharp lines.
And what quantum field the luminescence?
The light,
Yes.
the blue particles produce about 60%.
Oh.
The red ones, 30%.
Also very good.
But when you look at these, we don't have too many, very little inside. If you dry this, if you dry this and look, you say, where are they? Very little, because there's enough light coming out. Anyway, we're going to keep some, yes.
Sorry, you
Yeah.
mentioned the Samsung Corporation is one of your collaborators, so I have this more technical question. Is it possible to create a kind of LED display using the array of your particles of different sizes?
Explain.
Yeah, as RGB matrix or with external lightning or whatever, just that
Yes.
we use in our cell phones.
Yeah, that's what I thought.
Yeah.
I thought because the RGB, we could use their colors. Till I got visited by Wintec. You know, heard of Wintec? It's the fourth largest company. It's based in Taiwan, but has big headquarters in the United States. They are the fourth largest company that produces the screens for the cell phones. So I was telling them excited, telling them the colors. I said, we are not interested in the color. I said, what are you interested in? They said, we are interested in the electronic properties. Then they explained to me. The screens, first, a long time ago, early, were made of amorphous silicon, layer of amorphous silicon. That's why the calculators were very bad, you know, when you look at the calculator. Then they use techniques to improve on the amorphous to make it polycrystalline. So it improves and then nowadays they use a thin single layer of crystal, silicon. I said, what are you interested from me? They said, we want your nanoparticles to put them inside the amorphous layer and help the amorphous layer becomes crystalline as a seed, using very low power, because now they use lasers. And the people who use lasers have patent, big companies have patent and make contact there. So it's like, but then what is the idea? In each screen here, each pixel is a transistor, a thin film transistor. And so they want the nanoparticles to improve, but not the color. But in principle, you could use the different colors to shine and produce red, green, and black. That shows these nanoparticles are not only important for optical, like quantum dots, cadmium, selenium, but for electronics. You see, we built memory. Now they improve the transistor of a screen. The energy, conversion, for a catalyst. So it's really, once you put your hand on them, every time you touch them, you get something new. We're going to leave some. I brought with me enough to leave here with Dimitri, so he could send us copies. Welcome.
Okay, now maybe some questions and comments. Yes, thank you very much.
Thank you.